Welcome. Today, we're exploring the connection between humidity, particle generation, and product quality. I'm Dr. S.K. Singh, and together we'll uncover how these factors interact and why understanding them matters for improving outcomes. Let's dive in. Let's start by understanding relative humidity, or RH, which is simply the amount of water vapor in the air compared to the maximum it can hold at a certain temperature. Humidity plays a big role in many factors. It affects how particles form and move, how static charges build up, and even the moisture content in products. It also influences microbial contamination and overall product stability. For pharmaceutical cleanrooms, the typical RH range is between 40 and 60%. This range strikes the right balance, keeping contamination in check while protecting the product. When we talk about regulatory expectations, there are a few key standards to keep in mind. The EU GMP Annex 1 calls for strict control of environmental conditions, constant monitoring of critical parameters, and a solid contamination control strategy. ISO 14644 focuses on particle control, ongoing environmental monitoring, and maintaining cleanroom classifications. The FDA's CGMP rules remind us that environmental conditions must never compromise product quality. Across all these, one principle stands out: humidity limits need to be backed by science, driven by risk assessment and product needs. Let's talk about how humidity affects particle generation. When relative humidity drops below 30%, particle generation ramps up significantly. Why? Because low humidity boosts static electricity, increases friction between materials, and causes surface charges to build up. This all leads to more particles shedding from common sources like personnel garments, packaging, plastics, and powders. For example, in a capsule filling room, when humidity was lowered from 45 to 25%, the particle count shot up about 3 times, all driven by electrostatic attraction and friction. Let's talk about static electricity and how it pulls particles toward surfaces. When the air is dry with low humidity, it doesn't conduct electricity well. That means static charge builds up on operators, equipment, and packaging materials. Particles then get pulled in by this static charge, sticking where they shouldn't. For example, a plastic container at 25% humidity can hold up to 12,000 volts of charge, but at 50%, it drops to just 3,000. More static means more particles attracted, which raises contamination risks, especially for sterile products, dry powder inhalers, and injectables. Let's talk about how high humidity affects particle behavior. When the relative humidity goes above 65%, moisture starts to cause trouble. Particles absorb water, stick together, and sometimes even get a thin layer of condensation on their surfaces. This creates bigger clumps, or agglomerates. For example, powder particles that measure about 10 microns at 40% humidity can grow to 35 microns at 75%. The result: problems with flow, segregation, and overall product inconsistency. Let's talk about how moisture can impact product quality, especially for sensitive products like antibiotics, dry powder inhalers, lyophilized formulations, and effervescent tablets. These products risk serious defects, including potency loss, chemical breakdown, failure to dissolve properly, and inconsistent weight. For example, an effervescent tablet stored at 70% relative humidity absorbed moisture too soon. This triggered an early reaction, lowering its active ingredient level and ultimately causing the entire batch to be rejected. Moisture control isn't just important, it's critical. Let's look at how particle counts changed between two conditions. Under condition A, with 45% relative humidity, the average particle count was 7,000 per cubic meter. In condition B, at 25% humidity, the average dropped to 2,500 particles per cubic meter. That's a significant difference, an increase of 180% when humidity rises from 25 to 45%. These numbers come from multiple samples, showing consistent results across the board. This example helps us understand how environmental factors impact particle levels. Let's look at how we calculate moisture uptake in a product, using a simple example. We start with a powder weighing 100 grams. After exposing it to 75% relative humidity, the weight increases to 103 grams. To find moisture uptake, we take the difference, 3 grams, divide it by the original weight, then multiply by 100. That gives us a 3% moisture gain. Even a small increase like this can change how uniform the blend is, affect how it dissolves, and reduce its stability. When we face a humidity excursion like this one, several actions become essential. First, we need a deviation report to document what happened. Then, a product impact assessment helps us understand any potential effects on quality. Additional environmental monitoring ensures the situation is under control. And finally, implementing corrective and preventive actions, or CAPA, helps stop it from happening again. The risk assessment shows us which factors pose the greatest threat, with open product exposure, sterile operations, and moisture-sensitive APIs all rated high risk. HVAC failure is medium risk, but still important to watch. Let's talk about contamination control strategies, the backbone of maintaining a clean and safe environment. First, engineering controls like HVAC systems, dehumidifiers, humidifiers, and HEPA filters work behind the scenes to manage air quality and moisture. Then, monitoring systems keep a constant eye on conditions, tracking humidity and particles in real time, often with trending software to spot patterns. Operational controls focus on the human element, controlling material flow, enforcing gowning rules, and routine cleaning. For example, installing a humidity control loop cut relative humidity swings from plus or minus 12% down to just 3%, and particle excursions dropped by 80%. That's the kind of impact these strategies can have. When it comes to regulatory expectations, there are several key points we need to meet. Limits on relative humidity must be scientifically justified. Monitoring has to be continuous, with HVAC systems fully qualified. We also need particle and environmental monitoring, clear plans for managing excursions, and a risk-based contamination control strategy in place. Humidity levels play a huge role here. Below 30%, static electricity and particles increase, raising contamination risks. Between 40 and 60%, conditions stabilize, contamination drops, and product quality improves. Above 60%, moisture causes particle clumping, microbial growth, and product degradation. Managing this balance is critical. Humidity, particle generation, and product quality are tightly connected. When we control humidity well, we reduce electrostatic particles, avoid moisture-related contamination, and keep cleanrooms up to standard. This protects pharmaceutical products throughout their life cycle and ensures we meet strict regulations from the EU, WHO, FDA, and others. Too low humidity sparks static and particles, while too high encourages microbial growth. Staying within the right humidity range is key to clean environments, product integrity, and consistent manufacturing. It's a vital part of compliance and patient safety. Thanks for joining me today. If you want to dive deeper or have any questions, don't hesitate to reach out. I appreciate your time and attention, and I look forward to continuing the conversation. Thank you. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.